Welcome everyone. In this presentation, we will examine the quadratic formula, a cornerstone of elementary algebra and a fundamental instrument in mathematical analysis. It provides a systematic and universally applicable method for determining the roots of a quadratic equation. In mathematical problem solving, our objective is to identify those values of the variable that render an equation true. Quadratic equations as second-degree polynomials inherently admit up to two solutions. The quadratic formula ensures that these solutions may be obtained with clarity, precision, and logical consistency. A quadratic equation is a polynomial equation of degree 2 characterized by the presence of a squared term. Its canonical form is expressed as ax squared plus bx plus c equals 0. The coefficient a must be non-zero, for its absence would reduce the equation to a linear form. The constants a, b, and c govern the structure and behavior of the equation and play a decisive role in determining its solution. Although certain quadratic equations may be resolved through factorization, such an approach is neither universal nor always efficient. Many equations resist straightforward factorization, while others become unnecessarily cumbersome to solve by trial methods. The quadratic formula transcends these limitations by offering a definitive and general solution technique. Its universality renders it an indispensable tool in both theoretical and applied mathematics. The quadratic formula establishes an explicit relationship between the coefficients of a quadratic equation and its roots. Once the equation is expressed in standard form, the coefficients may be substituted directly into the formula. This structured procedure eliminates ambiguity and facilitates the accurate determination of solutions irrespective of the equation's complexity. Each constituent of the quadratic formula possesses distinct mathematical significance. The term minus b denotes the additive inverse of the linear coefficient. The plus or minus symbol signifies the existence of two potential solutions, reflecting the fundamental nature of second-degree equations. The expression b squared minus 4ac, also known as the discriminant, governs the character of the roots. The denominator 2a appropriately scales the resulting values. The discriminant serves as a powerful analytical indicator. Its value enables us to infer the nature of the roots without computing them explicitly. Defined as d equals b squared minus 4ac, the discriminant reveals whether the solutions are real and distinct, real and repeated, or complex in nature. This insight enhances both conceptual understanding and computational efficiency. When the discriminant assumes a positive value, the equation yields two distinct real roots. When the discriminant is 0, the equation possesses a single real root of multiplicity 2. Conversely, a negative discriminant introduces imaginary quantities, resulting in a pair of complex conjugate roots. The presence of the plus or minus symbol ensures the emergence of two solutions in every case. This observation accords with a fundamental theorem of algebra, which states that a polynomial equation of degree 2 has exactly two roots when multiplicities and complex solutions are considered. The quadratic formula is particularly advantageous when factorization proves impractical or insufficient. Its reliability and generality make it indispensable in academic examinations, scientific modeling, and applied problem-solving contexts. Whenever precision, consistency, and universality are required, the quadratic formula stands as a method of choice. In conclusion, the quadratic formula constitutes a central pillar of algebraic methodology. Its universal applicability, coupled with the interpretive power of the discriminant, renders it an essential tool for analyzing quadratic equations. A thorough command of this formula not only simplifies computation but also deepens one's appreciation of the structural elegance inherent in algebra. Thank you for your attention.